All right, so today we're going to start our second to last topic with the course. We have two more things left. The first is diffraction. So we're going to discuss kind of the larger theory of diffraction, why waves spread out and interfere, and eventually connect this to the diffraction experiments you already know, double slit diffraction, single slit diffraction, and kind of connect this to the properties of waves, and also see if we can kind of put together a general theory that will allow us to predict what the diffraction pattern, the bright and dark fringes, will look like given different types of shapes of openings. So we consider circular fringes or circular apertures, and consider what the constructive and destructive fringe pattern will look like for a square aperture rather than one long, narrow, rectangular slit. So that's our goal for the next probably week, so 3, 4, maybe 5 lectures. Today we're going to start, there's not going to be really many problems today. So what I'm going to do is build up a theory where on Monday we could come back and actually do some example problems. So today's going to be a lot of setup, really, but I think it's important and interesting to see the background. So there's going to be a lot of integrals today and approximating them. And if you're taking hard copy notes, I'm going to I'll tell you what you need to copy down, and I'm going to try to keep the mathematical insane details to a minimum and hopefully get the physics across. But I suspect this is going to kind of be a hard thing to do online, but we'll do our best. So diffraction fundamentally is the property of a wave that makes a wave bend around corners. So essentially, it's what causes a wave to spread out when it hits a small opening. Usually with most light sources, we can't see this because they're too big. With a small light source, kind of like we have shown here, we could see as the light, we could see kind of a spreading out effect of the image as light goes around these corners. The wave we have a almost plane wave that hits dead on that eventually then spreads out on the other side as a spherical wave. However, if our light source is big, the bigger light sources have this kind of spread out and shadow that gets kind of, the shadow, then the edges are not sharp on an object that is not a point light source. And the kind of spreading out, blurring of the shadow effect ends up hiding any type of interesting diffraction pattern you might see. So this is really something you only see with like smaller point light sources or true plane waves. But it is something we can still see in nature. And it's a property of all types of waves. So kind of as an example here, this is a picture from a beach in Tel Aviv where, just kind of a bit offshore, they have these things called wave breaks that are basically supposed to stop large waves that are coming in, kind of like waves that are too large and dangerous. But what it ends up acting like is here it acts up like a double slit interference source. But the thing that I want to highlight here is how the waves, when a wave comes through one of these openings, and there's another one down here on the far right, the waves come in essentially as plane waves, but when they hit the opening, they end up bending around the corners and spreading out as spherical waves, like you can see here. And this spreading out effect is, in particular, what diffraction is. This is the effect of light spreading out around a corner or after it passes through a small opening. And it's a property of all waves. It's not unique to light. You could see this with sound. You could see this, obviously, with water waves. We're going to focus on light, of course. The interesting thing that happens for us is that once we consider diffraction here, as these waves from different apertures or openings spread out, we have effectively 2 or 3 different wave sources. where the crests and troughs can now overlap and cause interference. So for light, diffraction effects can give rise to interference fringes, bright and dark, constructive and destructive fringes of light. For a water wave, that would change the amplitude of the wave at different points along the beach. If you're on a line where the crests are canceling out the troughs, you won't really have much fun surfing. If you're on a line where all the crests are lining up, that's where you want to do your surfing. So this is a nice picture that kind of shows at least diffraction happening in a mechanical wave. I think it shows the effect pretty clearly. So in order to see this effect, really what you want is this opening that the wave passes through to be about the same size as the wavelength of the wave you're talking about. So for instance, for water, those openings can be quite big because the wavelengths are quite long. If we want to see this effect with light, the openings we send light through, the apertures that we're hitting with light, have to be quite small. So for visible light, we're talking apertures on the order of hundreds of nanometers, so fractions of a micron. Very small, hard to manufacture, but not impossible. We have these things. And as you probably did in modern physics, you did the double slit experiment, or you may have done it in physics 112. But either way, you see that we can make slit apertures of this size and see this effect. Here, this is another picture from above of, I believe, a water wave source, but you can see the effect that if the wavelength is much smaller than the opening, you don't see much spreading out of the wave on the other side. As you make it bigger, you start to see more of this wave spreading out, becoming a spherical wave. And then if the wavelength's about the same as the aperture size, then you really definitely see this effect. So what we're looking at are water wave ripples on the surface of a tank. There's a wave generator over here with a light shining down from the top, and the crests reflect the light more strongly than the troughs of the wave. So that's how we're getting these photographs. The interesting thing, so the thing that we care about diffraction is the fact that once a wave diffracts, it will also cause interference. And this happens whether you have two slits and, as we'll see, even just one aperture. The wave that spreads out as a spherical wave will eventually form bright and dark constructive and destructive interference fringes. We're going to talk about why. It might not be as obvious for the case of a single slit as for a double slit, because you only have one source. But even if you don't have a slit, even if you only have light bending around a corner, if you're able to get a good enough photograph, you can still see interference fringes right around the edge. This is just a hand in the shadow of a helium neon beam. Here, this is kind of larger interference fringes from around light passing through a zinc oxide crystal. So again, this will happen with all waves, but measuring these interference fringes is something that is this general property of light waves. So and all waves. So in particular, seeing diffraction and in particular these interference fringes caused by diffraction is how we know something is a wave phenomenon, which is why the double slit experiment performed on an electron beam producing interference fringes is one of the experimental proofs of quantum mechanics, because it showed that electrons have wave properties. So diffraction is one of the key things. If you see this happening, you are dealing with something that has wave properties. And hence why we spend so much time studying it in physics, due to its connection, both the applications of interference and interferometers, but also just because it has this connection to connecting the physics of waves to the physics of quantum mechanics. So this is what we're going to talk about in the next few days. So from here, we're going to set up a diffraction problem, and we need to define some variables here. So here we have our incident plane wave coming in. We're going to call that E X, Y. And it's hitting an opening of some random shape. And we're going to consider light coming from a point P in that opening. That light then travels out, it diffracts and it spreads out, and it hits somewhere on our screen. It hits a point called P prime. So I know right now there's a lot of variables here, but we're going to have to keep track of them all over the next few weeks. But so this thing here, this first rectangle, is considered to be much smaller than our screen. And there's going to be two sets of coordinates that are going to be important to think about. One are the coordinates here, x, y, which we're going to use to describe whatever opening we have. We're also going to have a second set of positions, x prime, y prime, which are going to describe the bright and dark fringes we see on this screen. So that's the difference between x and y, and x prime and y prime. These are the coordinates on the observation screen. These are the coordinates on the plane of the opening or the aperture. The distance the light propagates from this point P to P prime, we can write using the Pythagorean theorem and these coordinates. So the z direction is the perpendicular direction, and we'll say that this plane is at z is equal to 0. So the distance in the z direction is z, and how far the wave spreads out in the xy plane can be written as this difference. X prime minus x and y prime minus y. We're also going to eventually have to get a function that describes what our opening looks like. So if we have a square opening, it would be a function that describes a rectangle in the xy plane. Or a square, obviously. If you have a square rectangular opening, the function txy will be a rectangular square function in the xy plane. If you have a circular opening, t of xy will be a function describing a circle. If you have a really, really narrow slit, t of xy might be a delta function, as you know from quantum mechanics. So that's what t of xy, that's what we're going to call t of xy. So we call it the transmission function, and basically where the aperture is open, t is equal to 1, and everywhere else on the screen, t is going to be equal to 0. So these are just kind of defining a lot of vocabulary and terms here. Does anyone have any questions about what any of these variables mean? Okay, over the next few classes, it's going to be admittedly a complete pain in the ass to keep track of all these variables, but we're going to do it. And we're going to kind of set up a method for, given the size and shape of our aperture, T, what does the pattern of our light on the screen look like? That will be E of x prime, y prime. We're always going to assume, for the sake of our class, that the incoming wave is a plane wave. Okay, so from here, we now need to set up, and we need to have some kind of theory that's going to predict, well, what's the light going to look like on this far side? And there's a principle from physics called Huygens principle, which is our starting point. So I'm going to animate that for you in a second. So here, we could come back to the slide later if you guys have any questions, but just make notes of these variables and what they are. We'll be coming back to this a lot to remind ourselves. So here's why, even if you have a single slit, that diffraction will give rise to an interference pattern. It was developed, it's called Huygens principle, named for the guy who originally discovered it, called Christian Huygens, who was a physicist and also poofy sleeve model. And he stated that basically if you have a plane wave, you could think of that as being made up of many different really small spherical waves. So like let's say if we had a plane wave here, a wave crest approaching our slit, that wave crest can be thought of as being made up of a lot of really overlapping, very closely small spherical waves that he called wavelets. Like this. And basically, all of the waves interfere with each other such that if they're all infinitesimally small, they effectively constructively interfere to make a straight line plane wave, or, you know, as close to a straight line as I can draw here. So what happens when when this plane wave then hits the opening? Well, all of these spherical waves hit and they spread out and they move through the opening. The problem is all of the spherical waves that were up here are blocked. And all of the spherical waves that hit here are blocked. So instead of having a long plane wave, the spherical waves right at the end here will just spread out, which causes the spreading out diffraction effect. So I'll do it one more time. And if we let them spread out far enough, these individual spherical wavelets will end up constructively and destructively interfering with each other, giving us an interference pattern. And the basic way to, if we want to calculate what this pattern will look like and predict it, we basically need to take Huygens principle here and make it mathematical. And that's what we're going to do today. And then on Monday, we'll have some examples where we apply the result. So what we have to do basically, if we want to find the pattern, the diffraction pattern on the far side of the screen, is we have to place our screen somewhere. So let's say here, and then add up the electric fields from all of these spherical waves that are coming from this opening. This can be done with an integral, as I'm sure you can imagine. When you want to add up a lot of very, very small things, you do that with an integral. So I'm going to put on the next slide the integral that expresses Huygens principle, and we'll talk through it. And admittedly, this is one of those integrals that's less something you can ever actually solve and more of one of those integrals that's really just an idea. So keep that in mind, and then we really got to make a lot of approximations before we can do anything with it. But if we wanted to state this mathematically, Huygens principle looks like this. Mathematically, it's called, the integral is called a convolution, if you're wondering. But basically what we have to do is we have to take all of our spherical waves. That's this function h delta x, delta y, or x prime minus x, y prime minus y, where the convention here is from our last diagram. Spherical waves from earlier in the semester look like this. They're exponent e to the ikr, and the amplitude drops as 1 over r due to conservation of energy. There's also going to be this, effectively this normalization constant with the wavelength that I'm not going to get into for the purposes of this class, but the main idea is that this function h is what's describing the spherical wave. So we want to add up all of our spherical waves, but we only want to add up the ones that actually make it through the opening or the aperture. So we want to multiply by that function that describes our aperture. So if the spherical wave hits a point where the screen is blocking the wave, t is 0, and that term doesn't contribute. Lastly, we need to know what the amplitude of our spherical wave is. And that's going to be, we're going to say that the amplitude of the spherical wave, at least at the beginning, is going to be equal to whatever plane wave we had coming in. So we're going to multiply by the amplitude here. And then we have to integrate over the entire screen that the wave is hitting. And here, the distance r is the distance, the propagation distance of the wave, and that's going to be taken from our last diagram. It's going to be the distance between the wave when it hits the aperture, and then the final point where it hits the viewing screen. So again, right now this is more of an idea and less of an integral that you can actually solve. But it's the mathematical statement of Huygens' principle. From here on out, this lecture is really, we have to make a lot of approximations to get an integral we can actually work with. And I'm not really going to go into all the details. It's a lot of Taylor expansions. And what I will do is after the lecture, when I post these slides, I will post the whole derivation. But I think it's one of those things that is really not going to have much point going over it online. But they're all kind of approximations that you guys have seen before. So let me put up, let me make some approximations, and I'll tell you what I did on the next slide. So there's lots of Taylor expansions that happen here, but basically what we have to do is we're approximating that distance r as being almost equal to z. The light is, of course, spreading out in the xy plane, but it's traveling more forward than it is out, even if it's diffracting. So that allows us to replace the r in the denominator of the spherical wave with z. The r in the numerator, or the r in the exponent, is this thing. So e to the I k r. This is an approximation for r as well. However, in the exponent, we can't just make the approximation that r is equal to z, because even if the change in x and change in y are small, the k vector might still be big. So this whole product in the exponent, you can't make this simple of an approximation. Instead, you have to do a Taylor expansion and do a lot of algebra and combining like terms, and you get something like this. And we still have our function describing our aperture, the amplitude of our incoming wave. If we factor out all of the quantities that don't depend on the integration variables, the x and y position along the aperture, we get something like this. All of this stuff just determines the amplitude of our outgoing diffracting wave. Usually we don't care about the absolute amplitude in a diffraction problem. We care where the bright and dark fringes are. So in some sense, you could kind of consider this like a normalization constant. It's determining the peak of our electric field, but that's not something we really ever care about in these problems. So the integral we need to solve simplifies down to this, which in the history of optics is called the Fresnel integral. And it's still not something you could ever really solve by hand. So we're not done with the approximations yet. However, it's one step closer. So this will tell us the amplitude of the light wave at a whole bunch of different positions along that screen. Though you can't solve it analytically, you can write some computer code to approximate it and use that to simulate diffraction patterns. So I think this is probably a good time to show you some of that to see what this looks like. So are there any questions on the idea here? Obviously, I'm not showing you the Taylor expansion or anything, but we're taking this Huygens principle, writing it as an integral, and trying to make approximations until we get to a point where we can do something with it. And we're almost there. So what I'm going to do next is kind of say we're not even going to care about the absolute amplitude or intensity of the light wave. We only really care relatively where it's bright, where it's dark. So this overall factor out front, it's not really going to concern us. What we care about is all still in this integral. So I'm going to renormalize the integral and just say that our outgoing amplitude when it hits the screen, the brightest peak, is just going to be equal to 1. Everything else will be a fraction of that, and what that does is gets rid of all of this mess. So we're going to ignore these factors, and this slide is kind of just saying what I was describing to you. So the Fresnel integral becomes this thing. Again, I wouldn't worry about copying down this integral at this point or anything. You're not going to be solving it, but it's a term that you might see come up a lot. The other thing we're going to do is we're always going to assume we have a plane wave with constant amplitude. So that allows us to take this EXY in the integral and pull it out and make it part of the normalization constant as well. So that gets rid of that E of XY. So summing up, the relative intensity or the relative electric field at positions along our viewing screen is going to be proportional to this integral. Where this integral is 0, we will have a dark fringe. Where this integral has its maximum value, we will have a bright fringe on that screen. So just showing you here some kind of simulation results, or kind of an idea of what this looks like. If you put a screen really close to the slit, you will see something like this. So we send that incident constant amplitude plane wave in. And the irradiance or the intensity versus position on the screen, if the screen is really close, will look something like this. Here it's a one-dimensional problem, so we're just doing the position x prime along the screen. You'll have these bright fringes, and then you'll have darker spots, but the intensity doesn't really drop to 0. It's still fairly high. So it's something this is something that's really hard to see experimentally, because the screen has to be really close, like on the order of a wavelength. As you move the screen further and further out, the diffraction pattern ends up starting to build into something we're more used to seeing in lab. So for instance, here for a single slit aperture, plane wave hits, all the different spherical wavelets start interfering, but as they spread out and we move the screen farther and farther away, so let's say like 10 times the wavelength of the light we're talking about, we end up getting one big center bright fringe. And that center bright fringe will be here. We get a dark fringe here and here, and then a weaker bright fringe here and here. And if you looked at the single slit aperture in modern physics lab, you might remember this pattern. If you haven't, well, you would have seen it in optics lab. But as you can see, as we make the distance z longer, we start getting the patterns we're used to seeing in lab. And mathematically, if we make the approximation that z is really big, that our screen is really far away from the slit, that allows us to take this integral that gives an intensity pattern we can't really solve for. But if z is really big, this integral, the integral that would give this pattern, is something we can solve. And in fact, it's a type of integral you've done many, many times at this point. And we're just one approximation away. So let's go back to the integral as we've had it. What we're going to do is assume, so d is going to be the size of the aperture. And again, the actual kind of numbers here are really something you could go through later if you want. But basically is what this is saying is that this last term in the exponent can be ignored if we're really far away from the screen, leaving just this guy. And what we can do, again, this is all stuff we're going to drop, but our integral simplifies even more. If we assume a constant wave, we could even, a constant amplitude plane wave hitting the screen, we could pull that E out. So really what matters, what we have to integrate is this guy. And these quantities, you'll notice there's these quantities of wave number times x prime over z, and wave number times y prime over z. We can write those a little bit more simply if we go back to our geometry for the problem. So if we look at this, our k vector, our total wave vector for the wave, points directly along the path the light follows. Sorry, give me this. So our wave vector for light going from this point here to this point here travels, looks like this. Remember, the wave vector k points along the direction the light we're considering is traveling, and its magnitude is equal to 2 pi divided by the wavelength, just as a reminder. But hopefully what you can see from this diagram is if, like, it's easier to draw for y prime, but if we want the y component of that k vector, it'll point upward like this. And this angle in here, we could use some trigonometry to get the y component of the k vector. But if the screen's really far away, we're going to make the assumption that this angle is very small. All right, and if we do that, basically what we can say, let me just go back here so I'm not drawing over what I meant to have appear, is that these angles in both the x and y direction are basically going to be equal to x prime divided by z and y prime divided by z. Here it's only drawn as a two-dimensional picture, but in the x plane, in the xz plane, and the yz plane, the same logic holds. So what that means is this quantity k x prime divided by z, that's the x component of the wave vector for our wave. Ky prime over z is the y component of our k vector. And that allows us to see what this integral actually is. So we're going to go back to that integral and replace these terms with the x and y component of our k vector. So using this result, we get what's called the Fraunhofer approximation of diffraction, one better than the Fresnel approximation. And this is an integral that can actually be solved. You have an e to the I kx times a function integrated over x. Here we also have a second direction, but that second direction, there's just another e to the I ky dy. So what we're doing here is multiplying the function that describes our aperture or opening by a complex exponential and integrating over all of space. This is an integral you know, and one that you've definitely done before. It's called the Fourier transform. So basically, what this is saying is that as long as our screen is far away from the opening that is diffracting the light, if we could get a function that describes that opening and Fourier transform it, the Fourier transform will give us the pattern of bright and dark fringes we'll see on the screen, if we could just plot that Fourier transform. So I'm using here the symbol script f for Fourier transform as just like shorthand for this integral. So we are going to try this. I know this was a lot. There's a lot of theory here that even if we're all in the room, it's a lot to follow. But from here, the practical application of this starts. So for our next class, when we come back on Monday, I'm going to kind of leave this and let you guys sit on this and go through the slides. On Monday, we're going to come back and we're going to take a single slit aperture and a double slit aperture, find a function to describe it, and then Fourier transform it to get the diffraction pattern. So on Monday, we're going to see at least one, and if we have time, hopefully 2 examples of how this works, and then more examples on Wednesday. And you'll have some problems in the homework that follow along with those. So right now, the takeaway message from today is that diffraction pattern is given by the Fourier transform of the function that describes whatever opening your light's passing through. So it's a really nice general result. It works for light waves as well as any other type of wave. And it's nice to see the Fourier transform keep coming back again and again in all these different branches of physics. So here, if you guys want to sit on this or see the, this lecture is actually, these slides are based on kind of on a different textbook, the other one that I kind of go to. So in your email, you'll notice I sent you an email right before class with the chapter of that textbook that follows along with these slides. So if you want to read their approach, the textbook kind of starts with this integral and then goes back to the Fresnel integral. But practically, all of the problems you can actually solve are all from this integral onward. So from here, we're going to focus on this Fraunhofer diffraction, and we'll see how it works practically on Monday when we do some examples. So plan to come back on Monday with trying to work along with me and do some math. Okay, so any questions, concerns? Remember, the ray optics homework problems are due today. So if not, that's what I have for you guys today. And do the reading, take a look at the slides again, and I'll see you on Monday for problems.